Welcome to Understand the Math. In this video, we're going to learn about asymptotes of rational functions, a really important concept in algebra and pre-calculus. We'll look at some examples and learn how to determine if a rational function has horizontal, vertical, or slant or oblique asymptotes. And then we'll learn how to find them. Let's get started. Rational functions are ones that can be written as one polynomial divided by another polynomial. N of x is the numerator polynomial, and d of x is the denominator polynomial. N is the degree of the numerator polynomial, and a is its leading coefficient, and then m is the degree of the denominator polynomial, and b is its leading coefficient. Let's start with horizontal asymptotes. A horizontal asymptote occurs when the degree of the numerator is less than or equal to the degree of the denominator. I've made a chart here to make this easier. If the degree of the numerator is less than the degree of the denominator, that just means there is a higher power in the denominator. Then you're going to get a horizontal asymptote y is equal to 0. If the two degrees are the same, then there's a horizontal asymptote, and it's going to be equal to the ratio of the leading coefficients. And then if the degree of the numerator is greater than the degree of the denominator, there's going to be no horizontal asymptote. In practice, what you need to do when looking for horizontal asymptotes is you need to find n and m and then compare them. For any rational function, there can be 0 or 1 horizontal asymptote. You can't have two. Let's now look at some examples. We're going to do 3 examples, and what we're going to do in these examples is find the horizontal asymptotes if there are any. Let's look at our first function. It is equal to x divided by x squared minus 4. The degree of the numerator is n is equal to 1 because x is raised to the first power, and then the degree of the denominator m is equal to 2 because x is raised to the second power. In this case, n is less than m, so that means we're going to get a horizontal asymptote y is equal to 0. A horizontal asymptote just describes what's happening to the function as x gets really large or x gets really small. Mathematically, we're going to write this as the limit as x goes to plus or minus infinity of our function, x divided by x squared minus 4. Now, as x gets really large, it's going to be much bigger than a constant. So we can approximate this as x divided by x squared, just dropping the minus 4. And then x divided by x squared is just 1 over x. And as x gets really large or x gets really small, that's like taking 1 divided by a really big number, and that is going to equal 0, which is exactly what our horizontal asymptote is. Graphically, if we look at the picture down here on the lower left, we can see that our function does indeed have a horizontal asymptote, y is equal to 0. Let's look at another example. In our second example, our function is equal to 3x plus 1 divided by x minus 2. The degree of our numerator is equal to 1, and the degree of our denominator is also equal to 1. So these two are equal, and that tells us that we're going to have a horizontal asymptote, and it is going to be the ratio of the leading coefficients. So we can write that y is equal to a divided by b, which in our case is 3 divided by 1. So we end up with the horizontal asymptote y is equal to 3. Let's understand this asymptote a little bit better by understanding what's going on to our function as x gets really large or x gets really small. So we can write this as the limit as x goes to plus or minus infinity of 3x plus 1 all divided by x minus 2. And we can approximate this as 3x divided by x, because as x gets really big, it's going to be a lot bigger than any constant. And then we can cancel the x's out, and this just becomes 3, which is exactly what we got for our horizontal asymptote. Let's now look at our graph, and you can see that there is indeed a horizontal asymptote at y is equal to 3. Let's now look at our third example. In our third example, our function is equal to x squared minus 3x minus 4, all divided by x minus 2. We're going to do the same thing that we did for the first two examples. We're going to first look at the degree of the numerator. So n is equal to 2. And then our denominator, its degree is equal to 1. And we see that n is greater than m. And when that happens, we have no horizontal asymptote. And you can see in our function graphed right down here that there is indeed no horizontal asymptote. This function has what's called a slant or an oblique asymptote instead of a horizontal asymptote. Let's now learn about vertical asymptotes. A vertical asymptote occurs when the function is undefined at a point. This happens when the denominator is equal to 0 and the factor does not cancel. I'll show you exactly what this looks like. The equation for a vertical asymptote is x is equal to a constant, and for any rational function, there can be 0, 1, or more than one vertical asymptote. When you're working with a rational function, to find a vertical asymptote, there are 3 steps that you can follow. You're going to factor the denominator, you're going to cancel any common factors, and then you're going to set the remaining denominator equal to 0. Let's look at an example and see how this works. In this example, we are going to find the vertical asymptote or asymptotes, if any, of the following function. Let's walk through the steps that we've outlined above. The first step is we have to factor the denominator. Sometimes it's already factored and then sometimes it isn't. In this example, it is not factored, so we'll start by factoring it. Our f of x is equal to x minus 2, and then we divide that by x squared minus 4. This is the part that can be factored. We can factor this as x plus 2 and x minus 2 times x minus 1. And then what we're going to do for our second step is we're going to cancel any common factors. So when we look at our function, we can see that we have an x minus 2 in the numerator that cancels with an x minus 2 in the denominator. This gives us the function f of x is equal to 1, all divided by x plus 2 times x minus 1. The third step is that we are going to set our new denominator equal to 0 and solve for x. So we have x plus 2 times x minus 1 is equal to 0, and that gives us x is equal to minus 2 and x is equal to 1. And those are the vertical asymptotes. Let's look at the picture so that we can understand this a little bit better. We found that we have a vertical asymptote at x is equal to minus 2, and on our graph we can see that it's right there. And we also found that we have a vertical asymptote at x is equal to 1, and we can see that on our graph as well. The last thing I want to point out, and it's very small, but I want you to call your attention to this circle right here. That is called a hole because our original function, let's go back up here and look at it, it was not defined at x is equal to 2. So down in this picture, this little circle is called a hole or a removable discontinuity. And we always have to put it in our graph because our function is not defined at that point. Let's now learn about slant asymptotes. The last asymptotes that we're going to look at are called slant or oblique asymptotes. A slant or an oblique asymptote occurs when the degree of the numerator is exactly one more than the degree of the denominator. Let's look down here at our chart. When we have a slant or an oblique asymptote, n is equal to n plus 1. That just means the degree of the numerator is one more than the degree of the denominator. And then our slant asymptote is given by y is equal to some constant c times x plus d. For any rational function, there can be 0 or 1 slant asymptote. You can't have 2. When you're working with a rational function and you want to find its slant or oblique asymptote, what you have to do is perform polynomial long division or synthetic division. I know this is a hard topic, and I have a video on this if you need to review that. When you divide two polynomials, such as n of x divided by d of x, and you do polynomial long division, what you end up with is q of x, which is your quotient, plus a remainder divided by d of x. The quotient is your slant asymptote. It is equal to cx plus d. Let's look at an example and see how this works. In this example, we are going to find the slant asymptote, if any, of this function. Let's start by determining if we have a slant asymptote. And to do that, we are going to look at the degree of the numerator and the denominator. The degree of the numerator is equal to 2, and the degree of the denominator is equal to 1. So we have n is equal to m plus 1, and we have a slant asymptote. To find the slant asymptote, I am going to start by doing long division, and then I'm also going to do synthetic division just so that you can see how to do it both ways. Let's start with long division. What we do is we take our denominator, x minus 2, and we divide it in to our numerator, x squared minus 3x minus 4. We're going to look at our first term, x, and we're going to see what we need to multiply it by to get x squared. Another way to think about this is just take x squared and divide it by x, and you get x, and then we're going to multiply. We're going to multiply our yellow x times x, and we get x squared, and then we're going to multiply minus 2 times our x, and we get a minus 2x. Then what we're going to do is we're going to subtract. So our signs change. This becomes negative, this becomes positive, and we end up with minus 3x plus 2x, which is a minus x, and then this comes down, minus 4. Now we're going to do it again. We have to see what we have to multiply this x by to get minus x, and that's going to be negative 1, so we put a minus 1 up here. So x times negative 1 is minus x, and then we multiply minus 2 times minus 1, and we get 2. So we plus 2. Now we're going to subtract it. So our signs are going to change. This is going to be a positive. That's going to be a negative. And we end up with minus 6. Before we go on, I want to show you how to do this using synthetic division because honestly, I think that's easier. To do synthetic division, you start by making a corner. And then what you're going to do is you're going to look up at your denominator and you're going to put the number that's in your denominator here, but we're going to change the sign. So we're not going to put a negative 2, we're going to put a 2. And then we're going to look at our numerator right here and we're going to write down the constants that multiply the x's. So we have a 1, a minus 3, and a minus 4. Then we draw a line. Our 1 comes down. Now we multiply. We're going to multiply 2 times 1, and we get 2. And then we're going to add, and we get negative 1. Minus 3 plus 2 is negative 1. Then we're going to multiply 2 times negative 1, and we get minus 2. And we're going to add those, and we get minus 6. And this part here is our x minus 1. We can say that f of x is equal to x minus 1 minus 6 divided by x minus 2. You really don't have to worry about the remainder part because we're just looking for the slant asymptote. Our slant asymptote comes from the x minus 1. Our slant asymptote then is going to be y is equal to x minus 1. Let's look at the graph of this function to make sure we understand this. On the lower left, we have the graph, and you can see that it does have a slant asymptote, and it's this line right here. And that line is y is equal to x minus 1. And that's it. Let's recap real quick. When you have a rational function and you're looking to see if it has a horizontal asymptote, all you have to do is compare degrees of the numerator and the denominator. When you're looking for a vertical asymptote, you have to set the simplified denominator equal to 0. And then when you're looking for a slant asymptote, you're going to have to do long division if the numerator is 1 degree higher.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.